Well, I hope you enjoyed that short video. I was looking at my prepared remarks today, and I realized that most of what I was going to say was already said in the video. So I'll try not to repeat too much, although there are some important things that may bear repetition. So thank you so much for coming today. Good morning.
Morning.
Almost good afternoon. Thank you for coming. I hope you've enjoyed the lunch, and I know that you will enjoy the speakers that we have planned for you today. In just a minute or two, we're going to explain the process for today, the sequence that we have planned for you, all the different programs and events. But first of all, let me introduce myself. For those of you who don't know me, I'm Mark Stover. I'm the Dean of the Oviatt Library. And the Oviatt Library is the shepherd, cultivator of the WISE endowment. And WISE stands for Women in Science and Engineering. And the WISE endowment was started several years ago, back in 2009, by the generosity of Bonnie Campbell. Dr. Bonnie Campbell is Professor Emerita of Engineering here at Cal State Northridge. She was a professor and administrator for many, many years here at this university. She was a pioneer because I believe she was the first tenured female professor in the College of Engineering here at Cal State Northridge. And she mentored many, many women to go into STEM fields, primarily engineering, but also other related fields as well. And Bonnie decided many years ago that she wanted her legacy to live on through encouraging young women to go into the STEM fields and be successful, to make a mark, because especially in certain fields such as engineering, but also other scientific fields too, there's underrepresentation of women. And this has to do with societal issues and education. And Dr. Campbell really believes, as do all the members of the WISE board, that the more education we provide, and the more encouragement, and the more mentoring that we provide to young women, the more successful they will be in STEM careers. So speaking of the WISE board, there are several, in fact most of the board I think is here today. So can I ask all of you who are here on the WISE board to stand up and be acknowledged? Let me tell you a little bit about the WISE board. Dr. Campbell provided the financial means and the inspiration for women in science and engineering. The WISE board made up of 10 members who were successful professionals in their field, meet every month throughout the year, and we plan events such as this, and we brainstorm on how we can do outreach, how we can provide more resources for the library in the area of women in science and engineering. And we also plan the actual logistics of the programs. Speaking of logistics, there are several members of the Oviatt Library who've done a lot of work behind the scenes for today's event, and I want to acknowledge them as well. So for those of you who work at the Oviatt Library and have worked on today's event, please stand. So at this point, I would like to turn things over to the chair of the WISE board, Marilee Wheaton, and she's going to introduce our speaker and also explain a little bit more about the details and the logistics of today's program.
Thanks, Mark. I'd like to add my welcome to everybody here. We're really excited to have you all. So yes, I get the honor of introducing our speaker, but also to tell you how we're going to conduct today, because as you notice, we do have quite a good number of folks that are here, and we do have a limited space in the planetarium for the show at the planetarium. So actually what we're going to do is divide into two groups. So I'm going to introduce the speakers so everyone will hear the introduction. But then what we're going to do is we're going to divide into two groups, and we'll have folks that will escort you over to the planetarium. And what we're probably going to do, just to make it easy, is we're going to divide just down the center of the room. So, you know, we'll say that this first half, this half over here, we'll go over to the planetarium, and then this half over here will stay to hear the speaker. And then what we're going to do is each of the various events are the same amount of time, half hour, and then we're going to swap, and then the folks from the planetarium will come back here, and Karen will give the presentation again, and then the folks that have been on this side of the room will go see the planetarium event. And then at the end of the day, we actually have closing remarks from Helen Cox. Helen Cox, she is the head of the Institute for Sustainability here at Cal State Northridge, and so you're going to hear about how the college really believes that sustainability is very important, and she's going to talk a little bit about what the Institute is doing. So that will be closing remarks, again, for everybody that can come back and hear that. And so while we're over at the planetarium, Jen Tobias, who's the head of the planetarium, will be giving a show over there. So we have a number of distinguished speakers actually that will be conducting the various events. And also over in the planetarium, if there are any folks that do not want to see the planetarium show and or who are younger than 9 years old, we actually have a separate event related to sustainability and earth sciences to be conducted by Oda Lutz, but that will also be over by the planetarium. So
it's going to be in the library, and who's going to be there?
oh, okay, it's going to be here in the library.
We'll leave people up there.
Okay, so we'll leave people. So she'll be doing that here. So again, planetarium, as you know, it'll be darkened, and then there'll be the show. So if anyone would prefer not to be in a darkened environment, and or it has to be 9 or above to see the show. So if anyone less than 9 years old, they can go to the event here in the library with Oda Lutz. So that's the plan. I don't know, is there anyone that is under the age of 9? Or we all? Okay, so then it's really based on your interest. Yeah, maybe some of you have seen the planetarium before and prefer to participate in the event that Ms. Lutz is going to do. So, your choice is we'll have folks that will lead you to the various events. So again, that's the plan. After I introduce the speaker, then we'll go ahead and divide up the group, and then the first group will head over to the planetarium for the show. Any questions on the plan for today? Yes, Susan.
What room in the library will we be going to with Dr. Lutz?
So it's the music and presentation room.
Yes, it's the music and media room up on the second floor, east wing, and we will have guides to lead anyone there who wants to go. So just let us know out in the foyer area if you want to go to the presentation by Oda Lutz instead of the planetarium, and we'll lead you up there. Also, one other announcement, because we're filming today, I'd ask you all to, I was going to say darken your cell phones, but that's not the right word. Although it's an interesting metaphor. But if you could either turn off your cell phones or just put them on vibrate, that would be terrific. And I think that's probably especially true in the planetarium, but also true here in this room as well. So I'm going to turn this back over to Marilyn.
Good. Okay, so I'd like to introduce our speakers. So the theme today is on sustainability, and part of the objective of being able to help your sustainability is actually accomplished via satellites. And Karen Yuen, she is the Science Data Applications Lead for the Orbiting Carbon Observatory 2, the OCO2, so satellite mission. And she's been working with NASA for 12 years. She works at the Jet Propulsion Laboratory, which is one of the NASA centers. She works closely with the science team, where she helps devise ways in which the mission's scientific data can be used by people within the wider community, ranging from research to other agencies to also citizen scientists. So the data that they collect It's used by a wide variety of people to understand the Earth better and therefore enhance the sustainability of the Earth. And previously, Karen managed the mission's education and public outreach activities as well. As you may be aware, as part of NASA's funding, they do put aside funds for the STEM and outreach area, and they very seriously work for that objective as well. So in that, they really join us here at WISE and the objective in terms of getting the information out, and especially as related to the missions in terms of space, which is the NASA mission. So with that, I'd like to invite Karen to come up here, and she'll begin to give her talk. But before we do that, if folks are done eating, or if you need to make a quick stop to the bathroom, you probably can. But with folks that are going to be dining folks over the cafeteria, why don't we go ahead and this half, we'll go to the cafeteria, and then we'll see you back here in about a half hour, 45 minutes.
See you later. You can hold on to the drink, but get rid of your trash. Oh, here's a big trash bag.
This is going to be very interesting for me because I realized I'm going to separate the room. So, and I was thinking of how I was going to speak to everybody. And this makes it easier because it's like I'm in a new group of people, so I can kind of customize my talk as need be. My name is Karen Yuen, and I work with the Orbiting Carbon Observatory to develop it. And I have to say I'm very pleased that you guys took time. I know how busy everyone is, so it's very flattering to me, and I'm humbled that you took time out on a Saturday to come out and hear about this. So my objective today, since you came out, is to really answer your questions. I know you hear me talk, but I feel very strongly that when I do speak to people, that if I can, I answer your questions. If I don't know the answer, I'll definitely tell you. But hopefully you will walk away knowing a little bit more about this mission that I have been working on for actually 13 years. It's like having a child, literally. And I want to show you something. I'm wearing my logo polo, because we really love our logos and our polos. So if you can see here, when we originally had this done, we had an artist do it for us. And then when we had OCO2, because we actually launched OCO back in 2009, and unfortunately we had a launch failure. So we lost the original satellite. And but President Obama felt that the mission was important enough that we got funding, and we were able to rebuild the mission, and we just launched it in July. And so 5 years later, we rebuilt the instrument, put it on the launch vehicle, and we launched it. And to symbolize how important this mission was to us and what it meant, the artist actually added I don't know if you guys can see, it was added a phoenix so that we could come out so it's in the CO2. So that's something that's very special to the project. And Watching the Earth Breathe is a tagline that folks came up with over 10 years ago, because that's what we're doing. We're looking at the Earth breathe, at the CO2. And let me show you a beautiful picture that was taken. So we launched that on July 2nd at 2:56 a.m. It was, I have something funny to share with you. This beautiful picture that you see here, I'm glad I saw this because we saw nothing at the launch site. The fog was so thick. We were on council, we ran outside and we were waiting, and we were on a Delta 2, so it was really, really fast. And then we just sat there waiting, I could hear it, and all of a sudden, like, oh, It was over our heads, and it was thicker than soup, and so we saw absolutely nothing. No light, nothing. It was just like looking out pitch black. And getting wet, because there was so much fog, we were actually getting wet from the fog. So this picture is actually quite stunning for the people who got closer. And I put this at the bottom, just so you know about NASA missions, there's a reason we fly our missions. There's always science behind it. There's a reason we do what we do. In the case of OCO2, and also for OCO, we really wanted to have capability that did not exist before. And I wanted to point out that our primary science objective is to identify, as it says there, regional scale emissions and collectors. So we're looking at sources and sinks. So basically, do you know what sources and sinks are? No. Okay. Very simple. You have a source, it gives you something. You have a sink, it sucks up something. That's it. Around the Earth, all over the Earth, we have different parts of the land, the oceans. They act as sources and sinks. For example, the oceans. The oceans, because of the chemistry that happens, it becomes a source because there's the interaction with the air and you see what's going on. There's some decomposition, all that becomes a source of carbon. But water also dissolves CO2, so we're able to act as a sink as well. And the ocean covers over 70% of the surface area of the planet, so it's a major part of what we look at when we look at the equation that we're balancing. But it's pretty good at taking care of things, keeping things in balance. And but we know something is off, and that's why we need a mission like CO2 to look at what's going on, because we know that over the millions of years, things have been going up and down constantly, but we were able to pretty much balance it out and not have too many issues. But in the last 150 years, what we've noticed is that something's really off, and what we've seen that is in the atmosphere, that CO2, the concentration of CO2 has been climbing, and we're really trying to understand where is it coming from, okay? So let me go down one more. Let me show you a little video that I have put together with a former student at Caltech. She is now Dr. Rosenberg, and we're very proud of this little story we put together to tell you a little bit about CO2.
When it comes to carbon dioxide in the atmosphere, we've all heard a lot about where it comes from. But what happens to it once it gets there? Lots of things, actually. The atmosphere, oceans, forests, and soil are all constantly trading carbon dioxide with each other in a global exchange called the carbon cycle. Some parts of this cycle are sources of carbon, while others are sinks. All of these natural sources and sinks are pretty well balanced. Just as much CO2 comes out of the atmosphere as goes in. But now we've got a problem. Ever since the Industrial Revolution, we've been tipping the balance, adding a CO2 source without providing a sink to match. Some of this extra CO2 is being taken up by natural carbon sinks, but not all of it. And on top of that, the efficiency and availability of these sinks may change over time as they react to changing climate conditions and as we clear forest for agriculture or homes. If we want to know what's really going on with the carbon cycle and how it may affect climate, we need more information. After all, we can only manage what we can measure. That's where the OCO2 mission, the Orbiting Carbon Observatory, comes in, NASA's first satellite designed specifically to measure the global distribution of atmospheric CO2 from space. How will it do that? By measuring the sunlight that bounces off the Earth's surface. On its way through the atmosphere, this sunlight interacts with CO2 molecules in the air. CO2, like other gases, absorbs only certain colors of light. OCO2 is tuned to look at these specific colors, and by measuring the amount of light that's missing in each one, we can figure out how many CO2 molecules got in the way. As OCO2 orbits the Earth each day, it will make hundreds of thousands of CO2 measurements. This high measurement density will give us far more information about where and how CO2 is traded between sources and sinks. Plus, measurements collected over weeks and months will capture the variations due to seasonal changes, allowing us to watch the planet breathe. If we can understand better where these carbon sinks are and how they store carbon dioxide, we'll know a lot more about the processes that control the rise of CO2 in the atmosphere and what role it might play in our changing climate. So take a deep breath and get ready for OCO2.
So just so you know, I wanted to do an animation like this because we do really fantastic I think, fantastic animations and tell, great stories, but I am a child of Saturday morning cartoons, and Schoolhouse Rock. And I remember moving, and I was saying to Mark earlier, I moved to this country and I was learning English and everything, and I remember paying attention to Schoolhouse Rock, and I thought that was very, very effective. So I really wanted to do something very similar to that, because I think it's less intimidating when you try to tell something with an animation. And now if I could just get somebody to sing it or something like that. No, that was not happening with me, so let me see if I can make it come on. We can put, man, we can do a lot of things. So I'll just go for it. I have animations to explain things, but I really want this to be a dialogue. How many of you are teachers here that have already seen my talk before? You don't have any teachers?
I'm a teacher, but I haven't seen the talk.
You didn't see it? You haven't seen it, okay, because I know there were, I had done one talk in July when Susan's group had gone to JPL, and then I did another talk with somebody at the SNAP-HK workshop, and there were some folks that said, oh, we saw this, and I thought, oh, okay. Let me see, okay, so let's go back to this for a second. How many of you remember this from last year? I like to show this one because this literally is history in the making. Just so you know, if people didn't realize this, last May was the first time ever in human history ever reached 400 parts per million for CO2. And I know there are people that have said, oh, it's been higher, I'm just going to stop everyone right there. I'm going to say it one more time. It's the first time in human history. That's all you need to know. What happened with the dinosaurs? Great, we weren't around. Let's just take that out of the equation. Us, human history. I'll just leave it at that right now. Why 400 parts per million? That's something that's a little bit more interesting. I've asked that question because it begs the question, why do we care about 400 parts per million? And the honest answer I can tell you, it is a number. It's a round number because it basically has indicated that we have grown quite a bit since the Industrial Revolution. But it also says that in a very, very short time frame, we've grown exponentially, basically. And it's an indication that with the population growth, with the deforestation, with a lot that we're doing, we are having an effect on the planet, okay? And it affects us ultimately. Wherever you stand, politically, whatnot. Our jobs, when we fly this mission, is to that's why we're trying to get the information about the sources and things, why we're looking at where the carbon is going. Because we need to put the facts out there so the people who do make the decisions, they have the right information. And our former principal and investigator, who's now our science team lead, I thought he said it best, because we can only manage what we can measure. And that's what we need to start with first, because we're not doing that in a very good way. And so that's what we're doing. But these are from ground sensor measurements. We know it's 400 parts per million. That was the first time ever, and everyone's thinking, oh, maybe it's a fluke. This I just pulled yesterday. I have updated this. There's an organization. They do look at our data. And what we have seen consistently, it gives you an idea, since Dr. Charles Keeling started making the measurements in Mauna Loa, we have grown, you can see the curve. We've been growing steadily. But also if you look at month by month and year to year, we have been growing. What I can tell you is the 400 parts per million is going to become a norm. It's something that some people who with their climate models, they think that if you reach 400 parts per million, that might be the tipping point. Not everyone agrees on that. Nonetheless, we're getting to a point where we're seeing that what once was something like, oh, I hope we never get there, it's going to be the norm. At which point we started saying, okay, you know, where's the point of no return? And that's the question, that's what we're trying to find out right now. And this was just the latest, I pulled this up the other day, monologue, you can pull this up yourself on the website. They have it, they make measurements, they put up the plots, the numbers are all there. They do averages for the week, for the month. That's where we're at. When I started working on the project, just so you know, when we started talking about all this, we hovered between 376 and 380 when I started working on the project. So the idea that we were going to launch a mission hopefully before it reaches 400 parts per million to do the study is something that I remember hearing about, and it's already here. In fact, it happened before we launched, and I remember being very struck by that. So, on to the next animation that's saying, so what is going on with all the carbon?
It was a Friday evening, and I was about to head home after a long day of mining the data when I got a phone call. It seemed that there was a problem with our global carbon budget. The sources and sinks were trading their atomic number 6s around as usual, but the numbers just weren't adding up. We could pin down what was going into the atmosphere, from cars and planes and forest fires, but when we tried to track it further, we were coming up short every time. It was clear that someone was skimming a little off the top. My first instinct was to check up on the usual suspects: the oceans, the soil, and the forests. Any one of them might be stockpiling some extra carbon, poised to release it and wreak havoc on our planet in some not so distant future. The threat was real. Large, complex systems like these were known to trade on both sides of the carbon equation, emitting on the right hand while absorbing on the left. Which way it might go overall was anyone's guess, and the tiniest change in one of these transactions might flip a sink to a source. I knew enough to know we wouldn't want that. But then I ran into a problem. I'd been treating each suspect as a single entity, overlooking the full diversity of marine and terrestrial environments that call our planet home. There were too many forests, in too many locations, too much variability year to year for one person to keep track of it all. I was flummoxed, overwhelmed. This was a problem of epic proportions, and there was only one solution. I needed more data. It was then that I heard about OCO2, a NASA mission launching in just a few months that could really give me a leg up on the case. I've seen a lot of satellites in my time, but this one is different. It'll measure atmospheric carbon so well that PIs like me will be able to figure out who's trading it where and how much, even how that changes over time. With 100,000 or so new CO2 measurements a day, we'll finally get to the bottom of this missing carbon mystery and head into an uncertain future armed with a little more information than we had before.
I don't know if you've noticed, I get to work with some really fun people, so many things that we get to do. Now, hopefully this doesn't fly on me again. Yes. Okay. I like this one because I actually used it this summer to talk to some of the teachers, because we were talking about Earth system and why it's important to look at the Earth as a system. And then in the poster, I noticed that they talked about the land, air, and water part, because you really can't look at it separately. You know, it's all interconnected. And that's something that the teachers work on and talk to the kids and or any grade level actually, where they decided to, as far as the standards that they're measuring against. One of the areas that's a bit of a challenge, I think, is that we are an atmospheric instrument. That means we measure what's in the air. And the interesting thing that we have to realize is that when we measure the air, it really doesn't change that much. So we're measuring something that doesn't change that much. And why would we want to do something like that? Well, first and foremost, we don't want the air changing too much. We need it too much. We need to breathe. We're all walking around, we're breathing. If the air's changing all the time, we'll probably be dropping like flies, and that's not a very good idea. And where most of the chemistry and what's going on happens in the oceans and in the land. What we can say about the atmosphere is that you've heard how they call it a blanket. So if you imagine it's a blanket that covers us, it's what protects us, it protects us from the radiation in space and all that. Well, what's going on is that that blanket is changing because it's what covers the land, it's what covers the ocean. But the exchanges that's going on, the emissions, it's affecting this really delicate balance now. So basically, there's enough activity going on, there's enough changes, that it's actually changing the concentration or the makeup of the blanket. So that's what we're looking at. That's why we're looking, because initially, we're like, well, why would you just measure something in the atmosphere when it's supposed to be very stable? It is because of its inherent stability, and that we can detect variability, the changes that we're interested in seeing, because it's not supposed to change that much. So that's why it's, because what's going on with the land and all that, that we get a lot more information, but it's hard and it's complex. What we are actually starting with something that we can look at, and so we're looking at the atmosphere and we're looking at the CO2. I don't know if some of you have seen this before, but this is the idea, this is everything that's going on with the ocean, the ground, that's what we call the lithosphere, and the atmosphere, they call it a carbon store. But this just gives you an idea of what's going on with the carbon cycle and everything that is happening. And this is another chart that just shows it's all interconnected. You cannot separate it. You know, it's a domino effect. Not directly, because dominoes is just one direction, but if you can think about it, it keeps going. And one area that, if you guys ever get a chance to get someone who talks from the Soil Moisture Active Passive mission, which is launching in January 29th, I had previously worked on that mission, and our interest for that was based on the water, carbon, and energy, because those cycles are really about life. And I think for California, when we're talking about the water, you would think that water and carbon dioxide is not related. Well, it's very much related, because if you think about it, we look at trees and plants as being a sink, because plants take out carbon dioxide, right? Well, guess what shuts down if they don't have enough water? The photosynthetic activity actually naturally shuts down. Plants learn to turn that off when they go into stress, and stress comes from not having enough water. Okay? So if you think about the agricultural areas and the trees and all the other parts of California that has a lot of vegetation and has been a natural sink for us, as groundwater depletes and they have less water available for them, they're going to shut down their photosynthetic activity. That means they are less effective as a sink. So it is incorrect to think that one is not related to the other. And I like to point out, so that's the water and carbon exchange, but they do all that. All that is done with the energy. There's not energy is like a currency that they use. So it's all interrelated. You're looking at so when you see energy, heat, so that's an energy source. That's where you do the exchange. That's where it's coming from. So we just call energy as a broader term. And then I just want to show you, once again, to show the interconnectedness of all this. This came from the climate.nasa.gov website. They actually have some of these indicators for people. So this gives you a carbon dioxide chart, how it's grown over time. And the one over here, this shows the ice core samples that they have. That's the best that we have right now as far as how far back we can be able to trace the CO2 concentrations. And they have looked at the ice core samples and how they've grown over time. But aside from the CO2, what else do we see? We know that global surface temperature has been on the rise. Okay, we know that sea level has been going up. This is all parallel data. When you start looking at the system as a whole, something is off. And that's the one thing, if I can ask you to walk away from today, is what is going on? What's going on the planet? Why, and what else do we need to understand, and what can we do? And Helen, and we can talk about that a little bit later on. It's like, what's our role? What can we do to help be a part of the solution? And it could be land ice. Land ice is Antarctica. Sea ice, which is the North Pole and South Pole. We are seeing changes, and it's having an effect, and it's all happening at the same time. With the years, we can see patterns. And I just just want to point these out. These are all sourced at the bottom if you end up asking for the presentation. You can look this information up yourself, you can get the data. And I want to go very quickly just to show you how OCO2 gets its data. You saw a picture, but we actually show you, because we get information when it's absorbed from what's reflected from the sunlight, and that shows you how the satellite is flying. We use the beam because it indicates pretty clearly, but that's how we look at things. And then you see, we fly pretty fast, and you can see we turn off when it's over the night sky, because we actually need the sunlight. We're looking at what's reflected, because we're a grading spectrometer. And a grading spectrometer, if you think about it, you take a CD, you know, the back of the CD, and you hold it against the light, and then you see the prism. It's like what we're picking up. You know, we're just picking up 3 bands from that. That's what we're looking at. And why can we make these very, very high measurements? We can do it because literally you can see these skinny swaths that we can do. We make almost 100,000 measurements a day. That's huge. Daily, we're making maps. Does that mean we have, I shouldn't say map, and for saying that, it's not really a map. We're able to get the data. I can't say we're mapping. Why? Because we're looking at reflected sunlight. And last time we checked, we're covered with clouds all the time. We can't see the clouds, which means we get about 30 to 33% of the Earth, what we can see without clouds. So that's why we can't say we're mapping, because we're not looking through the clouds. So I can say maps because you can see Earth. And I wanted to point this out and why it's so important about this particular mission. This is our Japanese partner, GOSAT. They were so successful with this GOSAT mission, they actually got funding from the Japanese government to build GOSAT 2. GOSAT focuses on measuring greenhouse gases. And so it's a very important partner for us to be looking at the data together. Now, this was the best that GOSAT could provide for us for CO2 maps. Okay? It's not bad. Because if you think about it, before this, we really don't have global coverage for CO2. All the CO2 we look at right now, even with the Department of Energy, you know, EPA, when they talk about CO2 and the measurements, these are ground sensors. The nice thing is CO2 is pretty well balanced, I'm not saying balanced, well mixed. So that you can say, oh, I have put this sensor on top of this rooftop. I have put this sensor on top of this building. They can pretty much extrapolate and say, this is what we have for CO2 over an area. And we have enough of these. They can say, this is about how much CO2 is over ground. These are ground sensors. They're very accurate, but it's only for that area. We don't really have global measurements. The Japanese did it. They launched in 2009, right before OCO, and then when we had our failure, they were thinking, oh my gosh, we're the only one up there. This is the best map that was produced before, okay? Now with the launch of OCO2 and our coverage, this is the coverage we're getting. This is the difference, okay? I mean, we are talking global coverage. It is huge, and it's very, very exciting for the science community, and also for us to be able to finally understand what we're able to finally see, in a sense. And I was telling you a little bit, I want to wrap up here. This is something that's very exciting that is brand new. Everything we've talked about for OCO2 has been about atmospheric CO2. Well, one of the fun things that we discovered from the Japanese was that we were able to see photosynthetic activity from the plants. Remember I was telling you that, you know, about the drought and all that. Well, photosynthesis basically, when you do photosynthesis, there's a photon that's released. Well, we can pick that up from space, you see. And we discovered that with the Japanese on the GOSAT satellite for the instruments, we could see it. So we thought, well, we should be able to see the same thing on OCO2. And what we have found out is that is absolutely true. So now we are mapping photosynthetic activity as well, globally. Why is that important? Most of the maps that you see right now that we talk about plant health, for example, they're looking at color change. What we see over time is like, oh, this is browner, this is greener, this is, there's an area that's being cleared. We'll see that area being, when you see that it's brown. Well, that is through a color change that we see from the satellites. Color change can take up to 1 week for you to see if there's a difference. What we're doing now is that we are able to make daily measurements. Okay, so we're getting that sort of information. We're going to be doing a press conference in AGU in December, and they'll be able to talk some more about it. But that's a very, very exciting thing for us to be able to finally do, and in an area that I hope that my colleagues will be able to talk more about, is that finally we're able to directly measure plant health. I mean, that's huge. We're not just looking at like, oh, I think something's not right because it's browning. We can say something is not right because it's shutting down its photosynthetic activity. We can measure that on the global scale now. So that's very exciting.
What color is good from that? What color is bad? Is blue good and red bad?
So basically, that's one of the tricks. The color scales, we tell people like color scales, human beings, we like to see a variation in colors because it shows like, ooh, something is changing. What does it really mean? Very arbitrary. But in this case, what we're seeing is that as you go towards the red, there's less photosynthesis. And then when you see, so basically you see throughout most of the world, it's pretty stable, things look good. But what is, if you look at the time frame here, and this is where I have to apologize, I don't know which month this was that we're looking at, but it's probably summertime. What you see is that if you look across the equatorial belt, you see a lot of dryness there, but there should be a lot of rain. So that is, if this is not calibrated, so it's not exact, but it's enough that we need to look at that some more. Okay. So, and then with that, I want to thank you for your time, and I don't know when the others are coming back, and I want to leave some time for questions.
Is it possible to make a man-made sink? Or
I think it's always possible to do something like that. My question, of course, is just how big does it need to be for it to be truly effective? And what do you need to do to end up making that, if that, even the net at the end of the commissioning was even worth it, as far as the labor and what you need to make it? There's been, and I'm not super knowledgeable about this, I've only read it like most people. We've heard about efforts for carbon sequestration and how they want to do that, and there are just questions right now on how well that would actually work, because one of the ways is that they put it very deep into the ocean, and with the pressure in the ocean, CO2 actually, the gas becomes almost like a liquid. So you can actually keep it suppressed in the ocean. The question is that what if there is a problem and something, the containers or pipes or whatever they decide to use, it actually releases the CO2. All of a sudden you have a very high concentration of CO2 that wells up. And we know enough that with the ocean, if there are big pockets of CO2, you see the algae blooms and the dead fish. So that was an issue that some environmentalists were thinking about. That's what I've read. I don't know enough about it, but it is an issue. It is also very, very energy and labor intensive to do something like that.
How long will the satellite be like 50 measurements?
Hopefully a long time. When we design a mission, we have something that's called a prime mission, meaning that this is the nominal, this is the minimum that we should have flying. In the case of CO2, it's 2 years, but we have more than enough propellant, and obviously with the solar panels working to charge things back up, it could go for much longer. We would like for it to go much longer, and it would be nice for it to go, 5-10 years. That'd be nice.
I think you may have touched on this a bit, but I wanted to probe a little bit further. So we're experiencing semi-severe drought in the western United States right now, and I'm wondering if scientists have been able to discover any kind of direct correlation between the drought and CO2 emissions. Because when I looked at the map, it looked like photosynthesis was doing okay in the western United States, and CO2 levels were we're doing okay, but we do have a drought. So are droughts just cyclical and just the fact that we live in the desert, or is it related to all the other things that we talked about?
There are several topics that you have touched on that. So first, in asking if there have been any sciences that show correlation between the carbon dioxide and water, I don't know directly. I haven't seen that. I haven't actually checked the literature search to see if anyone's done anything like that. And it's also hard because you have to actually look at case-by-case scenarios. Usually when you publish about something like that, you look at a case and I do not personally know of any like that right now. The SIP map that you saw, it's uncalibrated. So yes, it looks like there are areas that's fine because in the summertime, we actually have healthy vegetation. Everything's working just fine right now. So all this map is showing currently is that we have vegetation there and it's taking up, and it's working, there's photosynthetic activity. What we really need to look at with this is over time how that changes and then actually check what the conditions are at the time as far as water depletion or water use. That's when you will get the full answers. This is just one piece of the puzzle. It's not the entire picture, but it's a very important part of the puzzle. And you were saying something about what can be done for the
I don't think I asked that, but that's a good
okay.
question. Yeah.
Well, that's an area that where my work comes in when we talk about applications. It's really hard because, when people say, my dad's back in Minnesota right now, and there are a lot of farmers back there. And one of the questions when my dad said, oh, my daughter works at JPL, she works for NASA, and everyone's like, ooh, congratulations. Parents get very proud when they can say stuff like that. And they're like, oh, but they're not doing anything for us. What have they done since they landed on the moon? It's like, but they do, because it's pretty sad if you think about it. It's like, oh, we've done nothing else besides landing on the moon. How? And then they say, oh, okay, fine, you have those things on Mars. Okay, those things, the rovers that we landed on Mars. But I don't work on Mars program. I work on the Earth program. When we start talking to people about satellites and with the kids, do you know how your cell phone works? He's looking at me like, wow. It's for satellites. You think about this, and I'm going to get on my soapbox for a moment. Most people don't realize, you have direct TV, you have cell phones because of satellites. They don't just magically happen. It's true. And it's just, where do you think those satellites came from? Well, the Army definitely in the mid-50s when they needed the weather satellites because they were interested in that. They actually worked at NASA and they created weather satellites. And then when they realized that it worked well, they could bring the cost down and transfer it to other agencies to keep operating that. And that's where it comes from. So, more. Oh, I know we're being filmed, so I like this. We do have an OCO3. Unfortunately, they kind of played a chicken and egg game with the budget, and they actually canceled it, hoping that folks would be like, oh, how could you do something like that? Well, no one's saying that right now, but actually we have OCO3 is built. It's kind of a you guys know Raiders of the Lost Ark, at the end of the movie when they kind of create up everything, and that's what we've done with OCO3 because it's supposed to go on the International Space Station, and then they say, nope, we're just going to hold off on this right now, so they created it up and put it away. And what's really exciting about OCO3 is, and I didn't touch on this, OCO2 flies in 3 modes. We look straight down, which is called nadir. We work in glint, so we're looking at what's reflected, and we also do something that's called target mode. And target mode is the way that OCO3 is going to fly. Target mode means that we can point to where we want to look at. That's really, really important because with that point of capability, you'd be looking at cities. We can look at certain areas. So with OCO2, we're doing a demonstration to say, hey, we really can do this. And there are a lot of people that are interested in saying, oh, so you guys can point somewhere. What can you see? And with the International Space Station, since it flies lower than where we fly, and the coverage that they get, we literally will be able to study certain cities at certain times as needed. And it just, what will be able to learn from that, I don't know want to touch on because it's just never, it's unheard of. I mean, talking about the Irving effect and all that, we'll get direct data and we can have something like that.
Why was Mauna Loa selected as the location to monitor CO2 emissions?
To the best of my knowledge, Dr. Keeling picked it because one, it was remote, two, it was very, very high, and it wasn't very populated. He wanted to have a source that was somewhere stable, away from a lot of people. And it was interesting, it was at the SNAP educator workshop, someone was from Hawaii saying, well, we have volcanoes there. I'm not a volcanologist, and I said that I guess the way the winds blow, they weren't going to have an issue with something like that. But that's where he's built it, and it's the longest existing single CO2 measurement that we've ever had. And without that, and it's what's incredible is that his son Ralph continues it. Upon his passing, his son continues that with the measurement.
I can see a lot of connections to maybe the study project or elementary school to maybe the curriculum where we actually have to take over and doing a project.
They're looking at periodic table in elementary school. What are the? Okay, all right.
Well, so is there anything available in terms of ideas for students that might want to do a project on
CO2? I'm trying to think. Last time I did this, I had Oda help me. She actually gave me the new Common Core standards by grade level, so I can kind of pattern it up that way. I don't have that in front of me right now. You're saying 5th grade? Is it in 6th grade they learn California, or they're not doing that anymore? So 4th grade. That's a good question. Let me think about that. It depends on what they're supposed to pull from it, and I can tell you. I need to look at what that is actually.
I got several ideas just from your slides, and I know that.
And these are available. These are all released. You guys can share it with folks since it's all been authorized. It's been released for parents and surveys and all that. And for some of them, I actually put their own YouTube channel on the JPL. It's on next YouTube channel, so you can actually look that up. Sometimes what it's doing for periodic table, I'm trying to think. Well, there are patterns in the periodic table. You have your series, you have your groups that you're looking at, and the understanding, maybe focusing on carbon. So if you're looking at carbon and where it is in the periodic table, why is it such a stable element? Why is it something that sits the basis of life? What would make it, that'd be a good one to think about.
I can see how this could lead into like a project-based learning because we're focusing in LA, we're focusing on the drought. We've had a drought awareness week, which turned into a whole month from K.
Sure.
And some teachers take it upon themselves to read, and it's something that I can see how looking at the drought can lead into something a little bit.
Well, think about, the whole, the connectedness of the water and the carbon cycle. But if they're learning about the periodic table, I think I would focus on one element. You're looking at carbon and understanding how it's very stable. It forms a covalent bonds, and with covalent bonds, it makes it very stable. And when you have stable molecules, it allows things to change, it allows things to interact as needed, kind of grew a little bit, and that's how life forms. And I would, that's what we have a carbon-based life form. I would ask the kids to kind of see, what are the advantages of having something like that. And it's very, very symmetrical too. That's something that organic chemists, I'm an organic chemist, that's what we like to talk about, is that it's very symmetrical. And there's, in nature, we like symmetry very much. So, But change comes from not having some issues, so something knocks it out. So it's just something for them to, it's an opportunity for them to analyze just naturally how something occurs and what will make it want to change. I would go down that path.
Okay, well, I expect the other group will be coming back soon, so I want to thank
I just want to say a couple words about Dr. Cox. She's the director, as you can see, of the Institute for Sustainability. She's a professor of geography. She has a PhD in atmospheric sciences from UCLA, and also master's degrees in atmospheric sciences and also computer information science. And she's been at CSUN for 15 years. So without any further ado, I'm going to present Dr. Helen Cox.
Okay, thank you, and I'll try to be brief because I know we're getting towards the end of the program here. So probably from my introduction. I'm somebody who has a pretty broad education in different aspects of science, and that's because I've always liked science, but I've always liked learning. So once I sort of learn something, then I want to learn something new. And so I've actually learned my undergraduate was in physics, I did a master's in computer science, did a PhD in atmospheric science, and now I teach in the geography department. So I've been all over the place. And now I learn sustainability here, and that's great because sustainability is everything. Everything about, you know, our use of resources and the way we live and how we can make a better job of that. And it involves the environment, but it involves social considerations, economic considerations, all of those things. So there's never a shortage of new things to learn, and that's what's so attractive about it. So, yeah, thank you to Karen. When we met at the beginning, I was telling her that actually we didn't sort of know that we were involved in the same project to some extent. I worked with some other people at the university here. We had a grant from NASA on climate change education for the last 3 years, and our project collaborators at NASA were the project scientists on the OCO project, so actually we worked very closely. We had some student interns from CSUN go work during the summers at JPL, and actually one of them landed a job after that and is now employed there, so it's been a very successful collaboration for us. And so when I was asked to wrap up today, I didn't know exactly what you would be covering in the 2 sessions that you had. So let me just say, you know, a couple of things about that. I really enjoyed the planetarium experience, and it really shows us, you know, the Earth is just this little thing floating out in space, and it's so precious, and it's so important, and it's the only place that we know of that sustains life in this manner. And, you know, trying to get that point across so that we understand how vital it is to preserve it. And I think that's something that, you know, that the planetarium sort of just puts us in this place with just this tiny, tiny thing floating around in the universe. And the reason that we have life on Earth, of course, is because of water, and we're one of the, well, so far we're the only entity in space that we know about where water exists in all 3 forms. It exists as a solid in ice, and it exists as a liquid, and it exists as a vapor within the range of the Earth's temperature, and that's why the Earth can sustain life on other places can't. And so thinking about why we're sort of the Goldilocks of the universe is just very, very interesting, and sort of putting us in our place there. So sustainability allows me to do that and to think about that. And then thinking about the OCO project and measuring carbon dioxide, of course, you know, a lot of you know that climate change is one of the greatest concerns that we have. It's a contemporary problem, you know, because of all the emissions that we're generating from human life. And so that's one of the threats to the planet, and we have other threats to the planet because of our population and because of the damage that we're doing to the oceans and the environment and everything else. So how can we teach our students about that and not make it just sound like one long string of disasters after another. And so that's something that I feel strongly about. I'm an optimist, but I care very much about the environment. I care very much about the planet. And so, how does one become optimistic in those kinds of circumstances? So I'm just going to, show you a couple of graphs. You've probably seen these sorts of things, from Karen or from the press or the media. And we know that our planet is warming at a rate that's higher than it ever has in the history of man, and probably the warmest since the Cretaceous period when the dinosaurs roamed the Earth. So certainly, since human habitation, the warming rate is just higher than we've ever experienced. And it just keeps going up and up, and it keeps going up and up because we just keep putting more and more carbon dioxide into the atmosphere. And if we look at how the climate has warmed across the whole Earth, it's not uniform. Some places are warming much more than others. The oceans are the slowest places to warm because they absorb a lot of the heat, but the heat capacity of the oceans is so massive that it takes a long time to change the temperature. So the land is warming much faster. And the higher latitudes are warming the most of all. And some of those higher latitudes have already warmed by, more than 1 degree Celsius or 2 degrees Fahrenheit. And that may not sound like very much, but we're talking about 100 years. And we hope that the humans are going to be around for more than a few hundred years. We'd like to be around for tens of thousands of years. And so we can't afford to keep warming at this rate. And it's not just, the world. California is actually warming faster than most of the rest of the world. And it changed, it's regional across California. Here we're warming at about 2.5 degrees Fahrenheit over the past 50 years or so. So the temperatures, it's going up everywhere pretty much on Earth, but it's going up even more here. And in the future projections are that it's going to keep on going like this. And if we look at precipitation changes, they're much more complex. But as a general rule, drier places are getting drier and wetter places are getting wetter. If you want to just know overall, that's a guiding rule. We're getting drier here, as we know. We've had the drought, we're still experiencing a drought. So what happens when the Earth warms but not warming uniformly is that weather patterns change. And cyclical weather patterns like the El Nino and the decadal oscillations. So there are oscillations that happen on time scales of a decade or so, things like that. And the patterns of those change because the heating of the Earth is not happening uniformly. So one of the things that will probably happen, is predicted to happen, is that we're going to have more persistent high pressures over the Sun Belt, the region around us. If there's more persistent high pressures, what that does is it pushes the weather systems further north, and that's one of the reasons that we are going to tend to be drier and that we're experiencing drought. So scientists don't think that this is just a sort of a one-off thing. It's probably going to be something that we're going to have to live with and manage. And so then you have to think about what's going to happen with our water resources and our snow, on the Sierras. That's our source of water here in California. So all of these things, are not very happy, not very happy thoughts. The average global temperature is predicted to rise something between about 2 and 4 degrees Celsius. So that would be something between about 3.5 and 7 degrees Fahrenheit. And that's by the end of this century. That's huge. That's a huge, huge change. And if we look at how those warmings are going to occur by the end of this century, if you look at, a graph like this is how much warming is going to occur. People can't really tell very accurately because we don't know what our emissions are going to be. It all depends how much carbon dioxide we keep putting out. It depends how much forest we remove or how much forest we plant. So there's all kinds of things that have to come into figuring this out. But if we carry on our current path, we're looking at temperature changes in this region that are as much as 5-6 degrees Celsius. That's 10 degrees Fahrenheit. That's huge. And how is that going to affect us? We already know how hot it is here in summer right now. So to think of those kinds of changes, and particularly to think about those changes in terms of what it'll do to our water supply. It's scary, okay? And not just for us. So sea level, projections of the sea level. If we get a rise of about 2 feet in sea level, okay, that's going to affect Florida more than it affects us, obviously. But think about the rest of the world. There's 3.8 million people who live in the Nile Delta who are going to be displaced by that sea level rise. Okay, that's massive. What's that going to do politically? What's that going to do, socially? What kinds of problems is that going to cause? There are the impacts that it's going to cause with snow melt and the hydrological cycle are massive. The Himalayan glaciers, if they start or keep on melting at the current rate, the water from those glaciers supplies over 1 billion people in Southeast Asia that rely on that water, the melting of that water in the summer, the refreezing in winter, etc. If we start losing some of that, what's going to happen at first is there's going to be massive floods as it melts. And then if those snow caps eventually disappear over centuries and centuries, then there won't be a water supply. So these things are very, very scary problems. So what do we do about all of this? Well, the first thing to do, we need to stop putting so much carbon dioxide in the atmosphere, right? That's the best solution. There are other things that we can try and do. We can try and capture and sequester carbon dioxide, and the only way that we know how that works naturally is from forests, from trees and plants. So one of the other things we need to do is to not cut down any more forests globally. We need to leave our forests and plant more forests. And then we need to stop producing so much carbon dioxide. And what the OCO project is designed to do is to tell us how we're doing on that, right? We need to be able to, in order to do anything, we need to be able to measure it and monitor it very, very closely. Because if we don't do that, some people say, oh, we just don't have enough data, we just don't really know that that's true. So we need to have that data, and we need to know where our emissions are coming from and how much the forest is taking up. And if we do plant more forest, how much more CO2 can the forest take up? Well, 80% of these greenhouse gas emissions that are causing the warming come from energy production and energy use. So, all the electricity, our transportation, industrial, all of that, everything that uses energy, our way of life is very, very geared around using energy for one thing or another. Heating, lighting, transport are the 3 big ones. And currently, only about 8% of that energy comes from renewable energy sources. And of those renewable energy sources, more than a third comes from hydroelectric power. And in California, and actually throughout most of the country, we just about dammed all the rivers that we can dam. There really isn't much more potential for damming and getting more hydroelectric power anymore. It's very, very little that we can expand in that area. So if we look at some of the other areas, things like biofuels, wind, getting energy from waste, getting energy from geothermal, getting energy from the sun. Some of those technologies have been used for a long time, and the potential is not as much as hydroelectric. But some of them, we have vast potential, particularly in the areas of solar and wind that have been largely unexplored recently. And, not very recent. I mean, the last 2 decades we've done a lot, but previous to that we haven't done very much. Whereas we've been damming rivers and getting hydroelectric power for the last century or so. So relatively new technologies. And this is kind of where I find optimism, because a lot has changed in the last 20 years, a huge, huge amount. In the last 3 years, we've tripled the amount of solar PV production.
Experimental kite-powered hydrofoils capable of more than 30 knots.
Hold on a sec. I know I need to do this. Oh, well.
Kites, I'm going to give you a brief history and tell you about the magnificent future of every child's favorite plaything. So, kites are more than 1,000 years old. The Chinese used them for military applications and
Can you hear that or not?
so they knew at that stage they could carry large weights. I'm not sure why there is a hole in this particular map. In 1827, a fellow called George Pocock actually pioneered the use of kites for towing buggies in races against horse carriages across the English countryside. Then, of course, the dawn of aviation, all of the great inventors of the time, like Hargreaves, like Langley, even Alexander Graham Bell, inventor of the telephone, was flying this kite, were doing so in the pursuit of aviation. Then these two fellows came along, and they were flying kites to develop the control systems that would ultimately enable powered human flight. So this is, of course, Orville and Wilbur Wright and the Wright Flyer. And their experiments with kites led to this momentous occasion where we powered up and took off for the first ever 12-second human flight. And that was fantastic for the future of commercial aviation, but unfortunately it relegated kites once again to be considered children's toys. That was until the 1970s, where we had the last energy crisis. And a fabulous man called Miles Lloyd, who lives on the outskirts of San Francisco, wrote this seminal paper that was completely ignored in the Journal of Energy about how to use basically an airplane on a piece of string to generate enormous amounts of electricity. The real key observation he made is that a free-flying wing can sweep through more sky and generate more power in a unit of time than a fixed-wing turbine. So turbines grew and they now span up to 300 feet at the hub height, but they can't really go a lot higher. And more height is where the more wind is and more power, as much as twice as much. So cut to now, we still have an energy crisis, and now we have a climate crisis as well. You know, so humans generate about 12 trillion watts and 12 terawatts from fossil fuels, and Al Gore has spoken to why we need to meet one of these targets. And in reality, what that means is in the next 30 to 40 years, we have to make 10 trillion watts or more of new, clean energy somehow. Wind is the second largest renewable resource after solar, 3,600 terawatts, more than enough to supply humanity 200 times over. The majority of it is in higher altitudes above 300 feet, where we don't have a technology as yet to get there. So this is the dawn of the new age of kites. This is our test site on Maui, flying across the sky. I'm now going to show you the first autonomous generation of power by every child's favorite plaything. As you can tell, you need to be a robot to fly this thing for thousands of hours. This makes you a little nauseous. And here we're actually generating about 10 kilowatts, so enough to power probably 5 United States households, with a kite not much larger than this piano. And the real significant thing here is we're developing the control systems, as did the Wright brothers, that would enable sustained long-duration flight. And it doesn't hurt to do it in a location like this either. So this is the equivalent for a kite flyer of being in the snow. That's tracing your name in the sky. And this is where we're actually going. So we're beyond the 12-second steps, and we're working towards megawatt-scale machines that fly at 2,000 feet and generate tons of clean electricity. So you ask, how
there's a lot of people out there doing things like that. Has anyone seen Elon Musk's latest idea for the Hyperloop transportation tube? So he has this, I don't know if we can do, this is a minutes, I don't know if we can do this one, but this is something he just announced.
Between, say, Toronto and Montreal, maybe at some point you thought there must be a cheaper, faster, more efficient way. Well, the billionaire inventor says he has an answer, and today he unveiled his plans to shuttle people between nearby cities at ultra-high speeds using tubes. Lindsay Noco gives us a look at Hyperloop.
The whole idea feels like something you might see in a space cartoon. People packed into a pod, blasted across hundreds of kilometers in mere minutes. Sounds like the stuff of fiction, not science, but consider the source.
I have a name for it. The name for it's called Hyperloop.
That's Elon Musk, the man behind PayPal, the electric car company Tesla, and private space company SpaceX. Today, Musk released blueprints for a pod-style bullet train. No tracks needed, just a tube held up by pylons, using airflow similar to a good old air hockey table, and the same engineering principles that helped suck mail through tubes back in the day. Musk figures passengers could travel from LA to San Francisco in about 30 minutes. Maximum speed, a smooth 1,200 kilometers an hour. A far better plan, says Musk, than the California high-speed rail line currently in the works, with conventional tracks and a price tag of about $60 billion. He figures Hyperloop would cost just a tenth of that and travel more than 3 times as fast. Other companies are working on similar plans. This Colorado inventor has built a prototype, but experts say, slow down a minute.
I wouldn't be surprised if someone tries to take this on in the next few years, but it's going to take a very long time for anyone to actually build something that works.
Problem is, Musk is pretty much the only guy with the cash and the engineers to make this happen. And while he may build a prototype, he's busy with cars and spaceships, so trains could take years. But he's put the idea out there, open source, in the hopes that someone will take the idea and make it fly. Lindsay Noco, CBC News, Los Angeles.
Most of you ever traveled between, say, Toronto and Montreal, maybe at some point you thought there must be a cheaper, faster, more efficient way. Well, the billionaire.
So that's what I think the future is. That's what I think it's a better future. I think it's a future. You can look at the future, you can be an optimist or a pessimist. The future is the young scientists that we have here today. The future is one of cleaner energy, better, cleaner transport, better, cleaner cities, and it's all possible. People have started working on it. There's plenty of opportunities out there, and they're all exciting opportunities. So I wish you all the best for making that a reality.
So thank you, Helen, for that really interesting and optimistic presentation on our future and on sustainability. Thank you all for coming today. We really appreciate it. It shows that you care. It shows that you want to learn. And it shows that you really have a desire to change our future. So I hope that you enjoyed all the presentations today. And I hope that you'll look for future presentations from the WISE Living Science and Engineering Endowment. So we'll stay in touch. Thank you again. Yes, that's right. Oda Lutz from JPL has another announcement.
And on your way out, we have some handouts for you to pick up, and so it's like one per person, and grab those. And if you're a teacher or someone with a high interest in the CO2 mission, we have just a limited number of handouts of those. If you come see me, I'm happy to give you one.